This repository houses programming solutions for an infectious disease simulation project that was developed using C++ and a Linux development environment. The purpose of this project was to achieve a basic understanding of how an infection propagates through a population by running simulations under a variety of different conditions using object-oriented programming constructs. Pseudo-random number generator functions were used to generate probability values, select infected members of the population, and to update the health conditions of members of the population. These randomly generated parameters were treated as a substitute for reading in real-world probability data from the literature, thus constitutes a generalized understanding of how a disease spreads through an fixed population, rather than being tailored towards simulating the progression of a specific disease. With the GitHub repository cloned locally on my Mac machine, I'll go ahead and run through the development and execution of the simulations in real time and provide a summary of the important findings. So in our repository, we have our parent Infectious Disease Simulation Project folder. If we navigate into this directory, we have a directory with our source code, as well as the technical report that was assembled for the project. So the header file contains a library of class definitions used in each of the simulations. In this header file, we first define a class person for storing class properties such as name, disease status, and disease indicators specific to each individual in the simulation. We then have defined getter and setter methods for updating and returning the health status of individuals given their contact with others in the population, as well as several functions for setting infection thresholds and infecting healthy persons of the population using these pseudo-random number generator functions. The second class is defined in the population. In the header file is the population class. It's used to track disease propagation for a group of individuals in the population, reading in a vector of person class definitions. We then have associated getter and setter functions, similarly for updating and returning the health status of the entire population. Functions for setting disease propagation thresholds, such as vaccination percentage, and criteria for infecting healthy persons in the population. Starting with exercise 1, the simulation infects a single healthy and non-vaccinated person for a fixed number of days and tracks their state until recovered from the infection. So here we're prompted to input the name, a string of an individual whose health condition is to be monitored. And we have a daily list of strings that characterize the health status and vaccination status of this individual in the simulation. We see the first 24 days, the individual is healthy, not vaccinated, contracts an infection on day 25 with 5 days to go before recovery, before ultimately recovering from the disease on day 30. Exercise 2, the simulation extends the first case to a population where a single member of the population is infected each day, and the simulation was run until every member of the population had recovered from the infection, where no transmission of the disease was permitted. So let's set the population to a small number of, let's say, 1,000. Exercise 3 builds on the former by allowing a single individual infected by the disease to spread the infection to neighboring members of the population each day under a fixed probability of disease transmission upon contact. And it was again run until every member of the population recovered. Different simulations were run under various probability values and population sizes with an objective to identify cases where members of the population actually escaped becoming infected. So identify ranges of these parameter values wherein members of the population avoided being infected. So we set the size of the population, we set a probability value representing the probability of disease transmission upon contact for members of the population. That's fixed during the simulation. And we have a day-by-day representation of the quantity of individuals that are infected, the number that are vaccinated, and the number that have recovered from infections. Simulation Type 4 updated Simulation Type 3's criteria by allowing for multiple people in the population to be vaccinated at the beginning of the simulation, and the effect of the vaccination percentage on the spread of infection from a single individual was investigated. So set the population size at 10,000 this time. Let's set the percentage of people to be chosen randomly for vaccination to be a realistic number, let's say 25%. And the probability of disease transmission upon contact to be, let's say, 50% or 0.5 again. Lastly, in Simulation Type 5, each member of the population was permitted to contact a fixed number of people on a daily basis as opposed to a single neighboring person in the population. A number of simulations were run while varying the percentage of people vaccinated and the probability the disease was transmitted upon contact. The duration of the simulation is a function of the percentage of the population that was vaccinated. For a fixed population size, number of daily contacts, and probability of transmission was an important relationship in the study. In this study, the concept of herd immunity was studied, which states that if a large enough number of a population is vaccinated from a particular disease, then some people who are not vaccinated will never end up contracting the disease. So to test this theory of herd immunity, let's set the percentage of people that are vaccinated to a sufficiently high number of 95%. Probability of disease transmission upon contact to be 20%. So we can see that in this case, there are a large number of people in the population that are not infected at any point during the progression of the disease. Transitioning to major findings from the study, as we can see from the graph, for a fixed population size of 100,000 and infection probability 50%, the duration of the disease propagation, or the amount of time it takes for the disease to infect all healthy and non-vaccinated members of the population, varies exponentially with vaccination percentage. R-square value of 0.84 modestly reinforces this relationship. The graph also shows that an inflection point or critical threshold exists right around a vaccination percentage of 65%. After this point, the disease propagation is greatly slowed, so this would be considered a target vaccination rate of sorts by health authorities to mitigate the spread of an infection should this model a real-world scenario. It was then found that in general, for a fixed population size and infection probability upon contact, the duration of the disease propagation will have an approximately exponential relationship with the vaccination percentage. So this trend was extended to other combinations, realistic combinations of population sizes and probability of infection upon contact. Now, for the most realistic simulation type considered, simulation type 5, the relationship between vaccination percentage for values greater than 95%, and contagiousness of the disease or probability of infection upon contact was studied to satisfy the condition of herd immunity for a population size of 100,000. Again, herd immunity is the condition upon which there are members of a healthy and non vaccinated population that escape being infected. So, to enable a simulation where members of the population never become infected under different infection probability rates shown in figure 23, the vaccination percentages would need to be very, very high, between 95% for a 2.5% infection rate to 99% for a 20% infection rate, making this scenario pretty unrealistic in practice under the prescribed methods of contact and population size. Shown in figure 24, it was determined that the percentage of the population that must be vaccinated to satisfy this herd immunity condition increases linearly with the probability of infection, again for these high vaccination rates of between 95% and 99%. It was studied for rates below 95% and determined to be pretty impractical, as the probability of infection would have to be under 2.5%, which is very unrealistic in practice that any disease will have that kind of infection rate.